of let us I request Soham to start his lecture. Thank you.
Yeah, thank you. First of all, I would like to thanks to the organizer for giving me opportunity to speak in this conference. And to Professor Kulkarni, wish you a very happy birthday. And I have been associated with him last 13 years. It always gives me enormous pleasure discussing mathematics with him. And I have learned so many things. Whenever I meet with him, I learned so many things. It is very difficult to express in words. So wish you a very healthy and creative life. Okay, so I will be speaking on Schur Index and faithful irreducible representations of metacyclic groups. And first part, the review of theory of Schur Index on group representation. Yeah. May I continue?
Soham, I have a small request to make.
Yes.
Could you start from the beginning?
Yes.
Yeah.
Yes. Yeah. May I start? May I start?
Yeah, sir? Please.
Okay.
Yeah.
Okay. So first of all, I would like to thanks to the organizer for giving me opportunity to speak in this conference, and to Professor Kulkarni, wish you a very happy birthday. And I have been associated with him last 13 years, and it always gives me immense pleasure discussing mathematics with him. I have learned so many things from him, and which is very difficult to express in words. And yeah, wish you a very healthy and creative life. So let's start my talk, Schur Index and faithful irreducible representations of metacyclic groups. The first part, I will discuss about the theory of Schur Index on group representations, and it's a part of joint work with Frobenius-Schur Kulkarni. And the second part, I will talk about faithful irreducible representations of metacyclic groups, and it's a part of joint work with Rahul Kiture, my friend. Yeah. Okay. So the outline of the talk, first I will give a brief introduction, and then I will review the theory of Schur Index on group representations. And then I will talk about faithful irreducible representations of metacyclic groups, and the Schur Index of faithful irreducible representations of metacyclic. And finally, I will talk about the degrees of faithful irreducible representations of metacyclic groups. And I will end up with an open problem. Okay. So let me fix some notations. Throughout my talk, G is a finite group, F a field, and Fg the group algebra of G over F, and V a finite dimensional vector space over F, and Nv the ring of entomorphisms of V, and odd V the group of, or GLV the group of linear automorphisms of V. For an irreducible F representations rho G into GLV, E suffix rho, we denote the corresponding primitive central idempotent in the group algebra Fg. And degree rho, this is the dimension, degree of rho, this is the dimension of the representation space V. And for a subgroup H of G, core of H in G, this is nothing but the intersection of all conjugates of H in G. So Isai Schur in 1902 work he handles with the case F to be C or F to be C or more general F to be algebraically closed field of characteristic 0. And Schur clearly understood that to extend this work in the general F of characteristic 0, it is much deeper and involves some arithmetic aspects. And in his work in 1906, he wrote a paper and observed most of the salient features. He did not have the advantage of the Wednes theory. With Wednes theory, to realize its relevance for the representation theory took some more years. And this is the paper of Isai Schur, where he discussed the representations of finite groups over the general field F of characteristic 0. Now, let us review the theory of Schur Index on group representations. So with Professor Kulkarni, we wrote a paper. The title is Schur Index and Extension of Witt-Berman's Theorem. So we review the theory of Schur Index. So the setup is G is a finite group and F is a field of characteristic 0. And we start from an irreducible F representations of G. Schur asserted that if you start from an irreducible F representations of G, you can think that as an representation over an algebraic closure of F, and which we denote it by F bar. It decomposes into distinct irreducible F bar representations, rho 1, rho 2, rho k, with the same multiplicity M. So that was his brilliant observation. Each irreducible appears with the same multiplicity, and the number M later was called Schur index of rho. So now we are going to look at the Schur index from the viewpoint of Wednes theory. So for that, we need some ingredients from the theory of semi-simple F algebra. So let D be a finite dimensional F algebra, which is a division ring, and Z be its center. So Z is a finite dimensional field extension of F. So D has a structure of Z algebra. Now, if you consider the dimension of D over Z, this is, as we have seen in the morning lectures of Professor Bakshi, the dimension of D over Z is a square. And we denote it M square, and D contains a maximal subfield C, and the degree of the field extension E over Z is equal to M. Now, if you take the tensor product D with E over Z, this is going to be isomorphic to M by M matrix ring over E. So it's a split E algebra. And the Schur index of the finite dimensional division algebra D may be defined to be M. And sometimes in the textbook it is called index of D. So now Schur index and Wednes theory. So we start from an irreducible F representations of G. Now the representation rho canonically extends to an F algebra homomorphism from Fg to Nv. So we still denote it to rho. So rho is an representations of the group algebra Fg. Now we denote D to be set of all those endomorphisms of V such that A commutes with rho G for all G belongs to G. And by Schur's lemma, D is a finite dimensional F algebra, and which is a division ring. And we call D the centralizer of G in Nv. The minimal two-sided ideal of Fg corresponding to rho is abstractly isomorphic to matrix ring over division ring for suitable N. So just a minute. So let Z be the center of D, then the degree of the field extension Z over F is equal to K, and E is a maximal subfield of D. Now, if you consider the group algebra ZG, we can think that to be FG tensor with Z over F. So it is a sum of certain number of minimal two-sided ideals corresponding to irreducible Z representations of G. Am I audible? Hello?
Yes, you are audible.
Okay. So now we take the simple component corresponding to rho, which is M and D. If you extend the base field from F to Z, then this is isomorphic to direct sum of M and D, and the number of copies appear in that decomposition is K, and we have seen that K is the degree of the field extension Z over F. In terms of representation, so V tensor with Z over F splits into K distinct irreducible representations of Z, say, namely V1 direct sum with V2 direct sum with Vk. So each Vi is a Z vector space, and which by restriction of scalar may be regarded as F vector space. So what is the dimension of V over F? So the dimension of V over F we can split in that way: dimension of Z over F times dimension of V over Z. But the dimension of Z over F, this is K, but the dimension of V over Z, so V is isomorphic to D up to the power N. So therefore therefore by dimension of V over D, this is N, and dimension of D over Z, this is M square, and which is nothing but K times dimension of Vi over Z. So rho tensor with Z over F splits into K distinct irreducible Z representations of G. Now, if you pick up one simple component, it would decompose into so in you start from an irreducible F representations of G, and D is the centralizer of G in NV, and Z is the center of D, and E is a maximal subfield in D. Then V tensor with E over F, this is nothing but V tensor with Z over F and tensor with E over Z. Now V tensor with Z over F, this is V1 direction V2 up to Vk, they are distinct irreducible Z representation. Now whenever you take the tensor with E over Z, each of the Vi decompose into M copies of Wi, and Wi are the irreducible E representations of G. So and M is the Schur index of rho. So that was the assertion of the Schur. Now we want to see the Schur index from the different viewpoint. Okay, so Schur index from a different viewpoint. So Reiner actually gives a different definition of Schur index. So previously we thought the we have thought the Schur index from the bottom to top. If you consider F to be bottom and F bar to be top, previously we have seen from bottom to top, but now we are going to see the Schur index from top to bottom. Means you start from an irreducible F representations and come to irreducible F bar representation and come to irreducible F representation. So for that, let rho tilde be an irreducible F bar representations of G, Let chi be the character of rho tilde. Now for each element G in G, chi G is the sum of eigenvalues of rho tilde G. Let U be the exponent of G, and chi G is a sum of uth roots of unity. So therefore, chi G is an element in the field, cyclotomic field, F adjoint with zeta U, where zeta U is a primitive uth root of unity. And this is the paper of Reiner, where he gave the definition of Schur index from top to bottom. Yeah. Let F chi be the extension of the field F obtained by adjoining all chi G's for all G belongs to G. And it is certainly a subfield of F adjoint with zeta U, and it is called the character field of rho tilde over F. Now, F adjoint with zeta U is an abelian Galois extension of F. And it follows that character field F chi is also an abelian Galois extension of F. Let A be the Galois group of F chi over F. Now, if you consider alpha compose chi, this is an irreducible character of G. So starting from an irreducible representation rho tilde, we have obtained the order of a many distinct irreducible representations of G over F bar. And any two of these representations are called algebraically conjugate or Galois conjugate. Now, let us denote Z1 to be the character field F chi, and E be the primitive central idempotent of rho tilde. Then certainly E is in, from the expression of primitive central idempotent, it is clear that E lies in Z1G. Then the minimal two-sided ideal Z1GE is isomorphic to matrix ring over the division ring D1, say. Now from the Wednes theory, we have seen that V1 is isomorphic to D1 to the power n that is a representation space of G over Z1. And Z1 is the center of D1. And the dimension of D1 over Z1 is the square. And if E1 is the maximal subfield of D1, we have seen that it can serve as a splitting field for D1. So the representation rho tilde is realizable over E1. That is, if we choose a basis, we can choose a basis of the representation space V1 tensor with E1, with respect to which all the entries of the matrices rho tilde G lie in E1. So, since the dimension of E1 over Z1 is M, and M is the least such dimension, we can take the second definition due to Reiner of Schur index as the minimum of the dimension of the fields E tilde over which the representation rho tilde is realizable. Now, remark is that the first definition means you start from an irreducible F representation, and we have defined the Schur index of rho. And the second definition, we start from an irreducible F bar representations of G, and we can talk about the Schur index of rho tilde with respect to F. These two definitions actually equal. So now, so the second definition precisely is like that. Let rho tilde be an irreducible F bar representations of G with character chi. Let F chi denote the field adjoining to F all the values of chi G's. G belongs to G. That means F chi is the character field corresponding to rho tilde over F. And if L is an extension of F in which rho tilde is realizable, then certainly the character fields contained in L, and we define the Schur index of rho tilde with respect to F as minimum of degree of the field extension L over F chi, and the minimum being taken over all fields L in which rho tilde is realizable. So let us see with one example. Okay, so let us take G to be quaternion group of order 8. And as we all know, this is generated by two elements X and Y. Order of X is 4. The relation between X and Y is Y square is equal to X square, and Y inverse XY is equal to X inverse. And Q8 has 5 irreducible complex representations. 4 are one-dimensional, and 2 are, 1 is two-dimensional. But all the 4 dimensionals, 4 one-dimensional representations is of Schur index 1 by the very definition of Schur index. But what can you say about the Schur index of these degree 2 complex irreducible representations? The degree 2 complex irreducible representations of Q8 in terms of matrix representation, we can rho tilde X is that 2 by 2 matrix I 0 0 minus I, where I is square root of minus 1. And the matrix for Y is 0 minus 1 1 0. And it is clear that that representation is defined over Q adjoint with I. All the matrix at entries belongs to Qi. So it is not difficult to check that the rho tilde is not defined over Q. Whereas if you take the rho tilde, direction of rho tilde means 2 copies of rho tilde, this is defined over Q. Therefore, 2 is the Schur index of rho tilde with respect to Q. And yeah, so now I will talk about the second part of my talk, the faithful irreducible representations of metacyclic groups, and how the theory of Schur index on group representations plays role in the context of representations of metacyclic groups. Okay. So, so the definition of metacyclic group is that G is said to be metacyclic if it has a cyclic normal subgroup K such that G quotient K to be cyclic. The good thing about metacyclic group is that it has a beautiful presentation. It is generated by two generators X and Y. Order of X is equal to M, and they have relation like y to the power s is equal to x to the power t, and y is conjugating on x by conjugation, y is acting on x by conjugation, y inverse xy is equal to x to the power r with certain relations. Say, for example, if you take dihedral group of order 8, this is generated by x and y, and order of x is 4, order of y is 2, y is acting on x by conjugation, and y that is y inverse xy is equal to x inverse, and it's a split metacyclic groups. It can be expressed in terms of semi-direct product. And if you consider the Q8, this is non-split metacyclic groups. Now, faithfully irreducible representations of finite groups. So a representation rho G into GLV is said to be faithful if it is injective. If the homomorphism is injective, then we can say this is a faithful representation. And the question is that, does every finite group possess an irreducible faithful representation? The answer is in general no. The necessary condition is the center of G should be cyclic. But the next question, is the condition sufficient? The condition of center being cyclic is not a sufficient condition in general. For P groups, for metacyclic groups, this condition is sufficient. In general, that is not true. Now, H.S. Sim in 1993, he proved the following theorem for metacyclic groups for the degrees of faithful irreducible representations of metacyclic group. The theorem is, if G be a metacyclic group with cyclic center, and A be a field of positive characteristic not dividing the order of the group G, means we are in a semi-simple situation. then all the faithful irreducible F representations of G have the same degree. And he, in that paper is the degrees of faithful irreducible representations of metacyclic groups. In that paper, he posed the question, is the above result true for the field of characteristic 0? And in a joint work with Rahul Kiture, we answered affirmatively the same questions over number fields. If F is a number field, and if we take two faithful irreducible representations of a metacyclic group, then we have shown that degrees of any two faithful irreducible representations of metacyclic groups are going to be the same. So the proof is going to be, I am going to explain what is the, in which way we have come to that conclusion. Okay, start G be a metacyclic group, and we start from a maximal abelian normal subgroup of G with G quotient K to be cyclic. Now the theorem is, if we take a faithful irreducible representations of G and you restrict that to K, and you pick an irreducible constituent of that restriction rho restricted to G to K, and I be the inertia subgroup of eta in G or stabilizer subgroup of eta in G, then by Clifford's theory, you can get the representation rho by the process of induction from an irreducible representations of the stabilized subgroup, and here we denote it to be theta. So rho is isomorphic to induced representation theta, rho is isomorphic to theta induced from I to G. And if you restrict theta to K, that is isomorphic to M copies of eta. But what is the interpretation of eta? What is interpretation of M? M is equal to the Schur index of any irreducible constituent of theta tensor with F bar over F. Or we can say M, by the first definition of Schur index, M is the Schur index of theta. So in that way, we can construct the faithful irreducible representations of a metacyclic group starting from an irreducible representations of a maximal abelian normal subgroup of G with cyclic. Now remark is that as a consequence of the previous theorem, if F to be F bar, means if F is algebraically closed field, then eta is going to be linear representation, means degree 1 representation. Hence, the stabilizer subgroup of eta or inertia subgroup of eta is K itself. So therefore, theta is going to be eta actually, and rho is induced from eta. Thus, over F, a faithful irreducible representations of G is induced from a linear representations of K. So any faithful irreducible representations of G in that case is going to be the index of K in G. Now, if eta and eta prime are two irreducible F representations of K with core-free kernels in G, then they have the same inertia subgroup in G or stabilizer subgroup in G. And this is the paper with Rahul Kiture we have written. Now, what can you say about the Schur index of faithful irreducible representations of metacyclic groups? So the theorem is, if G is a metacyclic group, F a number field, and if rho and rho prime are two faithful irreducible F-bar representations of G, then the Schur index of rho with respect to F and Schur index of rho prime with respect to F, they are going to be the same. Here, the condition is condition if a number field is important. So we have proved for the number field, but over general field, yeah, this is question. Now, what is the idea of the proof? Yeah, let me say some. Yeah, let K be a maximal. So our setup is let K be a maximal abelian normal subgroup of G such that G quotient K is cyclic. And we take two faithful bar representations of G, rho and rho prime. And we have seen in the previous remark that rho and rho prime you can get by the process of induction from a linear degree
hello.
one representation. Yes.
So,
yes.
Kulkarni sir wants to ask a question.
Okay. Yeah.
Could you just show the statement of the theorem again?
Yes.
Yeah.
Yeah.
Yeah, metacyclic.
Yeah.
Yeah, please go ahead.
Okay. Okay. So let K be a maximal subfield of maximal abelian normal subgroup of G such that G quotient K is cyclic. Now you take two faithful irreducible representations of G, say rho and rho prime. And we have just, in the previous remark, we have seen that rho and rho prime we can get by the process of induction from a one-dimensional representations of K and say lambda and lambda prime. So rho is induced representation induced from lambda, and rho prime is a representation we can get by the process of induction from lambda prime. Let chi and chi prime be the character of rho and rho prime respectively. One can show that the character field of chi and chi prime over F, they are going to be same, and character field of lambda and lambda prime over F, they are going to be the same. It's not difficult to prove that. Now we are interested in Schur index. So therefore, whether without loss of generality, we can take F to be F chi, and which is same as F chi prime. So that means that simple component corresponding to rho and rho prime, they are becoming the central simple F algebra. Now, since G quotient K to be cyclic, so suppose it is generated by YK coset, and which is isomorphic to CD, cyclic group of order D, then y to the power D commutes with all elements of K as well as Y. So therefore, y to the power D is a central element of G. And since the kernel of lambda and kernel of lambda prime, they are core free in G, then therefore that lambda of y to the power D is a primitive order of y to the power dth root of unity. So lambda acts faithfully, and similarly lambda prime. So without loss of generality, we can take lambda y to the power D to be zeta, and lambda prime y to the power D to be zeta to the power j, where j and order of y to the power D, they are co-prime to each other. So now let us denote E to be the character field of lambda over F, which is a cyclotomic extension. Now, now one can show that. So here F zeta over F. So this is a Galois extension, and this is, in fact, in that case, this is cyclic, and so one can show that conjugate representations of lambda conjugating by the element y, this is actually lambda sub sigma, and this is also true for lambda prime. Now, if you let E be the primitive central idempotent of EMF chi, so this is the Schur index times chi, And E prime is the primitive central idempotent corresponding to MF chi prime, chi prime. So therefore, FGE and FGE prime, they are the central simple F algebras. So now we know that so the index, Schur index of rho and rho prime with respect to F, they are nothing but the index of these two central simple F algebras. So, but by a theorem of Yamada, that first central simple F algebra FGE, that is isomorphic to the cross product algebra E gal E over F beta, and second central simple F algebra FGE prime, this is isomorphic to the cross product, a classical cross product algebra E gal E over F beta prime, where beta and beta prime, they are the factor sets and they are given by this relation. So they are, so beta is different from the beta prime. So beta sigma to the last relation, beta sigma to the power A sigma to the power B is equal to lambda of y to the power D, and beta prime sigma to the power A sigma to the power B, this is lambda prime y to the power D. Yes. And as I said, that Schur index of rho with respect to F, this is nothing but the central simple F algebra FGE, and which is isomorphic to the classical cross product algebra this, and Schur index of rho prime with respect to F, this is the index of the central simple algebra FGE prime, and which is isomorphic to the second cross product algebra, classical cross product algebra. And now an important fact is that if A is a central simple algebra over a number field F, so far in the discussion we did not use the F to be number field. Now we are going to use the F to be number field. If A is a central simple algebra over a number field A, then the order of the algebra A in the Brouwer group of A is equal to the Schur index or index. So using that fact, so the order of the central simple algebra FG in the Brouwer group of F, this is nothing but the order of the two cocycle beta in the second cohomology group of gal E over F with coefficients in E star, and the order of the central simple algebra FG E prime in the Brouwer group of F, this is the order of the two cocycle beta prime in second cohomology group gal E over F with coefficients in E star. And one can show that this order is going to be the same by, so the beta and beta prime, we have, this is the expression for beta and beta prime, and one can show that order of beta is going to be the order of beta prime. So this proves that the Schur index of rho with respect to F is same as Schur index of rho prime with respect to F. Now the final theorem is that if G is a metacyclic group, F a number field, and we take two faithful irreducible F representations of G, then the degree of rho is equal to degree of rho prime. That we are going to prove using the classical Schur's theory on group representations. So the proof is like that. So by classical Schur's theory on group representation, let rho, we can think rho to be a representation over a bar. So rho tensor with a bar over F from the Schur's theory, this is rho 1 direction, rho 2 direction, rho delta with the multiplicity Schur index. And rho prime similarly is rho 1 prime direction, rho 2 prime direction, rho delta prime with multiplicity Schur index. As rho 1 and rho 1 prime are two faithful irreducible F bar representations of G, then their degrees are same, that we have seen, and we, in the proof of the previous theorem, we also have seen that their character fields are going to be same. So the degree of f chi over f and degree of f chi prime, chi 1 prime over f, they are going to be the same. So this is, yeah, this should be chi 1. Now, and from the previous theorem that m f rho 1 is same as mf rho 1 prime. So from the above two equations, this follows that the degree of rho to be degree of rho prime. So this proves that any two faithful irreducible representations of a metacyclic group over number fields, degrees are same. Okay, so yes, so so an open problem from there so in the same paper we have proved that let G be a metacyclic group if a field of positive characteristics such that characteristic of F does not divide the order of the group G, and rho prime are two faithful irreducible F representations of G, then the degree of rho is equal to degree of rho prime. But the question is that what can you say about the general field of characteristic 0? So the problem is let G be a metacyclic meta-abelian group and F be a field of characteristic 0, and if rho and rho prime are faithful irreducible F representations of G, do they have the same degree? If we take two that we have found a counterexample for the two-step solvable group, this is not true. Say, for example, if you take G to be SL2F3 and the field to be Q adjoint with the square root of -1, there we can see the degree of two faithfully irreducible representations. One is of degree 2, another is of degree 4. So this is not true for two-step solvable groups. But then, yeah, the question is, what can we say about the meta-abelian group? If it is not true, how far it is true? Yeah. So thank you for attention.
Thank you, Soham.
Yes.
Any questions? Any comments? Soham,
yes.
the question is that Professor Kulkarni is asking if you could explain something more about the theorem 6.
Okay. Okay. So, yeah. So in theorem 6, we are in a semi-simple situation. So we have taken the characteristic of the field does not divide the order of the group G, and F is of positive characteristic. So in that situation also, degrees of any two faithfully irreducible representation, they are of the same degree. This is because the Schur index doesn't play a role, because in that we are taking the field to be positive characteristic, so Schur index is going to be 1. So therefore it only depends on whether the character fields of any two faithfully irreducible representations, they are going to be the same. And we have proved that they are actually same. So therefore their degrees are same. So the complex part, the Schur index, is not playing any role because we are in a field to be positive characteristic. Yeah. but so there we have to just show that the character fields are going to be the same. Yes. Maybe I'm not able to see. Yeah. Any question, or am I clear?
No, in your problem, I mean, the corresponding group algebra structure is so clear that you cannot, whether the Schur index, obviously the Schur index plays a role when characteristic f is 0.
Yes.
But then you cannot decide whether there are two faithful representations where the Schur indices are different or whatever.
Yeah. Can you, sir, repeat the question?
No. In characteristic f equals 0,
Yes.
you have this problem about the Schur index.
Yes.
Then, I mean, it should be possible to decide it quickly if you get in the meta-abelian situation. You have the structure of the group algebra.
Yes.
And whether you can have two different faithful irreducible representations.
Yes.
Whether the Schur indices are same or different, it should be possible to decide. I mean, I'm just saying vaguely. I do not know what the issues are.
Yes. So, okay. Actually, the issue is, see, in the case of metacyclic situation.
No, the metacyclic is clear. Now, the meta-abelian.
Yes. So there, just yeah. So in the proof that the central simple algebra FG is that isomorphic to cross product algebra, this is fine. But the what would be the order of that factor set, and what would be the relation between these two factor set beta and beta prime? That is not clear in the case of meta-abelian case, because finding Schur index from the expression, general expression of the cross product algebra, that is not so clear. Means it will be of the simple component will be in the cross product algebra form, but the actual Schur index computing that, in that case, relation between these two, relation between the order of the factors, this is the difficult thing. Here, in that case, it's a cyclic algebra. So we can pass from one to another, but in the case of meta-abelian,
First of all, for the meta-abelian case, it is difficult to have, more difficult to have faithful representations.
Yeah, that is one thing. And even if it has faithful irreducible representation, even if we have simple components.
So what is the restriction that if it has a faithful representation, what does it say about the structure of the group?
Yeah, so that is.
I think those are the issues that have to be.
Yes, but
you should be able to see through quick examples. I think when the irreducible representations exist, and if there are different irreducible representations, then what are the Schur indices?
Yes.
And I mean, it should be possible to see. I'm just making I'm not helpful here. Yeah.
Yeah,
Thank you.
yeah, you are right. So here, yeah, you are right that there is a beautiful expression of the simple components in terms of soda pair or in terms of cross product algebra. There is a
I see.
So it is possible to find the simple components, but finding the Schur index, because that cross product algebra is not in the matrix ring over division ring form. It's just a cross product algebra.
Look, if you have some examples of in the meta-abelian case, which are not metacyclic,
Yes.
and the irreducible representations,
Yes.
if it exists,
Yes.
you should be able to say something about the structure of the group also.
Yes. 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 True.
Yeah. So if you can show me, if you can point out offhand some examples.
Okay.
Yeah. Okay. I think it.
Yeah.